Agreement is a fundamental concept in measurement science and research methodology. Agreement refers to the degree of concordance or consistency between two or more sets of measurements or ratings. Ensuring reliable and valid measurements is crucial to research. High agreement validates the reliability of your measurement tools. When measurements show high agreement, results can be reproduced across different settings, times, or laboratories. Poor agreement, on the other hand, increases the risk of drawing flawed conclusions from your data. Agreement is assessed in two key applications. First, inter-rater reliability, which measures consistency between different observers. Second, method comparison studies, which determine if different measurement techniques can be used interchangeably. In a research context, agreement metrics help establish the validity of your measurement approach. High agreement indicates reproducibility across different settings. Throughout this series, we'll explore different metrics for measuring agreement, from simple percent agreement to more sophisticated approaches like Cohen's kappa and concordance correlation. Raw percent agreement is the simplest measure of agreement for categorical data. It is commonly used when analyzing categorical variables, such as shown in these pie and bar charts. The calculation is straightforward. We divide the number of agreements by the total number of observations, then multiply by 100%. Let's consider an example where two pathologists diagnose 5 tissue samples as either benign or malignant. They agree on samples 1, 2, and 5, but disagree on samples 3 and 4. In this example, the raw percent agreement is 3 agreements divided by 5 total observations, giving us 60% agreement. While raw percent agreement is easy to calculate, it has an important limitation. It doesn't account for agreement that might occur by chance alone. Raw percent agreement provides a foundation for understanding more sophisticated agreement metrics, which we'll explore in the following sections. Cohen's kappa, represented by the Greek letter chi, is a statistical measure used to quantify inter-rater reliability. It is a chance-corrected measure of agreement between two raters who are classifying the same objects or subjects. While raw percent agreement simply calculates how often raters agree, Cohen's kappa goes further by accounting for the possibility that agreements might occur simply by chance. This mathematical correction provides a more accurate assessment of true agreement than raw percentages alone. The formula for Cohen's kappa subtracts the probability of chance agreement from the observed agreement and then divides by the maximum possible value of this difference. In a typical scenario, two raters independently classify the same objects into categories. Kappa measures how much they agree beyond what would be expected by chance. Cohen's kappa uses a formula that accounts for chance agreement. In this formula, P0 represents the observed agreement between raters. PE represents the expected agreement by chance alone. Let's examine the complete formula, which appears as shown here. This formula is a chance-corrected measure of agreement. The formula adjusts the raw agreement by subtracting the expected agreement by chance, then dividing by the maximum possible value above chance. To measure agreement between raters using Cohen's kappa, we start by creating a 2x2 contingency table. This table is used when two raters classify subjects into two categories. In our example, these categories are disease and no disease. Let's examine each cell in the table. Cell A represents cases where both raters agree the subject has the disease. Cell B represents disagreement, where Rater 1 classifies the subject as having no disease, but Rater 2 says the subject has the disease. Cell C represents the opposite disagreement, where Rater 1 says the subject has the disease, but Rater 2 classifies them as not having the disease. Finally, Cell D represents cases where both raters agree the subject does not have the disease. Now let's populate our table with an example. Imagine a clinical study with 100 patients, where two doctors classify each patient. In this example, the diagonal cells A and D represent agreement between the raters. 30 patients were classified by both raters as having the disease, and 45 patients were classified as not having the disease. The off-diagonal cells B and C represent disagreement. In 25 cases, the raters disagreed on the classification. This 2 by 2 contingency table is the foundation for calculating Cohen's kappa. In the next step, we will use these cell frequencies to calculate the observed agreement. In a 2 by 2 contingency table, calculating P0 or observed agreement requires identifying cells where raters agree. The diagonal cells represent agreement between raters. In our example, 45 cases were rated as disease by both raters. Similarly, 30 cases were rated as no disease by both raters. To calculate P0, we sum these agreement cells and divide by the total number of observations. In our example, that's 45 plus 30 divided by the total of 100 observations. This gives us a P0 value of 0.75, meaning the raters agreed on 75% of the cases. Let's look at a real example showing agreement between two pathologists grading tissue samples. In this table, we can see the observed agreement is calculated the same way, summing the diagonal cells and dividing by the total observations. This observed agreement value is the first step in calculating Cohen's kappa, which we'll use to account for agreement by chance. To calculate the expected agreement, or p-trect, we need to understand what agreement would look like by chance alone. We'll use our contingency table with values A, B, C, and D and focus on the marginal totals. Marginal totals are the sums of rows and columns. They represent how frequently each rater uses each category. The expected agreement, p-string, uses these marginal totals to calculate how often raters would agree by chance. Let's see a real-world example of a contingency table with its marginal distributions. Using our formula, the expected agreement equals the product of matching marginal totals divided by the square of the total observations. In essence, PZAC represents how often raters would agree purely by chance if their ratings were completely independent of each other. Let's see a simplified example. If rater 1 marks 60% of cases as disease, and rater 2 marks 40% as disease, then by chance alone, they would agree on 48% of cases. The expected agreement value is crucial for calculating Cohen's kappa, as it allows us to adjust the raw agreement by accounting for chance agreement. Now that we have calculated PZ and P subscript E, we can determine Cohen's kappa. The formula for Cohen's kappa is P0 minus P subscript E divided by 1 minus P subscript E. Let's work through an example. Suppose we calculated that P0 equals 0.85 and P subscript E equals 0.60. We substitute these values into our formula. P0 minus P subscript E gives us 0.85 minus 0.60, which equals 0.25. For the denominator, we have 1 minus P subscript E, which is 1 minus 0.60, giving us 0.40. Finally, dividing 0.25 by 0.40 gives us a kappa value of 0.625. This kappa value of 0.625 represents substantial agreement between raters after accounting for agreement that could occur by chance. Here we can see Cohen's kappa values from a real study showing how agreement improves across multiple rounds of assessment. Remember, kappa values range from -1 to +1, with values above 0.6 typically considered substantial agreement. When interpreting Cohen's kappa, we use a standardized scale that ranges from -1 to +1. Values below 0 indicate poor agreement, which is worse than what would be expected by chance alone. Values between 0 and 0.2 suggest only slight agreement. From 0.21 to 0.4 indicates fair agreement between raters. Moderate agreement is represented by values from 0.41 to 0.6. Substantial agreement occurs when kappa falls between 0.61 and 0.8. Values from 0.81 to 1 indicate almost perfect agreement between raters. This standard interpretation scale is widely accepted in research and clinical settings. Remember, Cohen's kappa adjusts for agreement that might occur by chance, providing a more accurate measure of inter-rater reliability than simple percent agreement. Understanding the difference between correlation and agreement is crucial when analyzing measurements. Correlation measures the relationship between two different variables, while agreement assesses the concordance between two measurements of the same variable. In correlation analysis, we examine how one variable changes in relation to another. For example, how blood pressure might correlate with body weight. While correlation is a broader concept that can apply to many types of relationships, agreement is more specific. Let's consider some examples to clarify this difference. In a correlation study, we might examine how blood pressure relates to weight. These are different variables with potentially related values. In an agreement study, we might compare blood pressure measurements from two different devices. Here, we're assessing the same variable measured in different ways. The most important distinction to remember is that high correlation does not necessarily mean high agreement. For example, two measurement methods might show a perfect linear relationship, demonstrating strong correlation, but if one consistently measures higher than the other, their agreement would be poor. When selecting metrics for your research, understanding whether you need to measure correlation or agreement is essential for valid and reliable results. Scatter plots help us visualize the difference between correlation and agreement. Correlation measures the strength and direction of a relationship. As shown in these examples, correlation ranges from perfect positive to perfect negative, with various strengths in between. Let's directly compare agreement versus correlation with two different scatterplot scenarios. In perfect agreement, data points fall precisely on the line y equals x. This means both measurements produce exactly the same values. In contrast, correlation without agreement shows points that follow a clear pattern but don't fall on the y equals x line. The measurements are related, but not the same. Here's a practical example. Imagine two blood pressure devices measuring the same patients. The measurements are highly correlated with an R value of 0.95, but one device consistently reads 20 units lower than the other. To summarize the key points, high correlation doesn't guarantee agreement. Perfect agreement follows the y equals x line, while correlation without agreement means points follow a different line. Choosing the right metric is crucial for valid clinical and research decisions. Pearson's correlation coefficient, R, quantifies the strength and direction of a linear relationship between two continuous variables. The formula for Pearson's R might look intimidating at first, but we can break it down into manageable parts. Let's understand what each component of this formula represents. The numerator calculates the sum of products of deviations from the mean for each pair of data points. The denominator normalizes this value by the product of standard deviations, ensuring R is between -1 and +1. Pearson's R values range from -1 to +1, with different values indicating different relationships. Here's another representation of the formula that you might find in statistics textbooks. These scatter plots show examples of positive correlation, negative correlation, and no correlation between variables. Understanding Pearson's R formula is essential for properly interpreting correlation results in your data analysis. Lin's concordance correlation coefficient, or CCC, assesses how well two sets of measurements fall on the line of perfect agreement. While Pearson's correlation coefficient only measures the strength of a linear relationship between variables, it doesn't account for systematic differences. Lin's CCC improves upon Pearson's R by considering both precision and accuracy of measurements. Precision refers to how closely measurements relate to each other, essentially what Pearson's correlation captures. Accuracy, on the other hand, measures how close those measurements are to the true value, or in other words, the absence of bias. Lin's CCC offers several advantages over Pearson's correlation coefficient when measuring agreement between methods. It considers both precision and accuracy, specifically measures agreement along the line of perfect agreement where y equals x, and can detect systematic bias between different measurement methods. For example, two blood pressure devices could be highly correlated, meaning they're precise, but one might consistently read 10 millimeters of mercury higher than the other, meaning they're not accurate. Lin's CCC would detect this bias, while Pearson's R would not. To understand bias-corrected correlation, let's start with a simple example of perfect correlation. Here we have data points that fall exactly on the line of perfect agreement. Both variables have identical values. Now let's examine the same data, but with a consistent bias where y is always 3 units higher than x. Notice that these points have the same correlation as before. The Pearson correlation coefficient remains 1.0, indicating a perfect linear relationship. However, there's a systematic bias. Every y value is 3 units higher than its corresponding x value. While the correlation is perfect, the agreement between x and y is poor. The points no longer fall on the line of perfect agreement shown by the dashed line. This is why we need a bias-corrected correlation coefficient. Lin's concordance correlation coefficient accounts for both correlation and bias. Lin's CCC incorporates Pearson's correlation coefficient, but also penalizes systematic differences between the means of the two variables. The key difference is this term, which represents the squared difference between the means of x and y. As this difference increases, the CCC decreases. For our bias data, Lin's CCC is much lower than Pearson's R, accurately reflecting the poor agreement despite the perfect correlation. This makes Lin's CCC a more appropriate measure when we're interested in agreement between methods, not just correlation. Mean absolute error, or MAE, is a common metric for measuring the average magnitude of errors between pairs of observations. To calculate MAE, we start with paired data points that represent corresponding measurements or predictions. For each pair, we calculate the absolute difference between the actual and predicted values, which is the vertical distance to the perfect agreement line. The mean absolute error is calculated by taking the average of all these absolute differences. For our example, the mean absolute error is approximately 0.70 units, which represents the average magnitude of error across all data points. This visualization helps us understand error magnitude across all observations. Lower MAE values indicate better agreement between measurements. The formula ensures that all errors contribute positively to the final MAE value, making it a robust metric for understanding measurement agreement. The mean absolute error formula provides a way to quantify the average difference between paired measurements. The formula is defined as MAE equals the sum of the absolute differences between each pair of values yi and xi divided by n, the number of pairs. Let's break down each component of this formula. N represents the total number of paired measurements in our dataset. Yi and xi are the individual paired values we're comparing. The absolute difference, shown by the vertical bars, ensures we measure the magnitude of difference regardless of which value is larger. We sum up all these absolute differences across all pairs. Finally, we divide by n to get the average, giving us the mean absolute error. The MAE gives us the average magnitude of errors without considering their direction, making it especially useful for measuring agreement between continuous variables. Unlike other metrics, MAE treats all sizes of errors linearly, providing a straightforward interpretation of the average disagreement between measurements. The MAE plot is a powerful visualization tool that helps us understand the distribution of errors when comparing measurements. Let's examine a sinusoidal dataset with noise as our example. Creating an MAE plot involves 4 key steps. First, we calculate the absolute error for each data point. Next, we sort these errors from smallest to largest to understand their distribution. Third, we plot the sorted errors against their index or rank, creating a line graph that shows how errors increase. Finally, we shade the area under this curve, which visually represents the total error in our measurements. Let's visualize how an MAE plot is constructed. We start with axes, where the x-axis represents the sorted data point index and the y-axis shows the absolute error. We then plot the absolute errors for each data point, sorted from smallest to largest. Connecting these points creates a curve that shows how errors increase across the dataset. By shading the area under this curve, we visualize the total error. The shape of this curve reveals important information about error distribution. Different error distributions may appear in various categories of data. Here we can see how errors might distribute differently across 4 categories. The MAE plot is particularly valuable for identifying outliers, detecting systematic errors, and comparing error patterns across different measurement methods. To create a Bland-Altman plot, we first transform our paired data into 2 new values, the mean of each pair and the difference between measurements. For each pair of measurements, we calculate the mean as x plus y2 and the difference as y minus x. Now we can create a Bland-Altman plot by plotting the difference values on the y-axis against the mean values on the x-axis. Each point on the plot represents one subject, with their position determined by the mean and difference of their measurements. Next, we add a horizontal line representing the mean difference, which indicates the average bias between the two measurement methods. Then, we add the limits of agreement, which are typically set at 1.96 standard deviations above and below the mean difference. These limits help us identify outliers and assess agreement between methods. Here are real-world examples of Bland-Altman plots. These plots clearly show the mean difference as a horizontal line, with upper and lower limits of agreement, indicating where 95% of the differences between measurements are expected to fall.